yesterday, it doesn't matter what question B asks ultimately. I don't think there's a person in the room who doesn't recognize that the box is going to slide down the ramp, hit the other box, and land on the floor. Those three events are going to occur. Before I'm going to even start the problem, I'm going to try and identify what I think are appropriate physics principles that could be used to figure out some of these answers. For example, the box sliding down the ramp. I think I've got three choices, but probably only two that might work and one that will work. Like, I think you might approach this like maybe I could use kinematics. Well, that would only work if you had the acceleration of the block, and you don't. Well, maybe I'll use Newton's laws, right? It's an inclined plane. To use Newton's laws, you're going to have the angle of the plane. And we don't have that. Now, if they gave us the length of the plane, we might be able to get it, but we don't have that. So, you all saw that, right? Yeah. Well, because like only three of you reacted. And the three of you who reacted, I figured, are we all having the same problem that the rest of you aren't? So, that leaves us with only one other possibility, and that's conservation of energy, right? So I'm going to say, well, the first thing we could do conservation of energy. We could say we have, from let me just kind of put this like from here to a box that is here. Oh, no, that will not work. To a box that is here, from there to there, conservation of energy. Okay. Now, I'm also going to notice that box is going to strike the other box. So there's a part of this problem where there will be two boxes that will have some combined velocity while this box has a velocity before. That looks like a collision. So I think there's going to be a collision from there to there. We all okay with that? And then I see the clear projectile motion problem. Well, the box acquires a velocity, v0, by sliding down the ramp. I'm creating a variable that I'm going to use in the course of this problem. Because it may or may not be asked of me later, but I know that I'm going to have this velocity in order to somehow execute the collision that's going to occur. Right? If I want to make a prediction of what's going to happen, this velocity will help us establish the momentum of the box just before the collision. And I know after the collision, the boxes will likely have a different velocity due to what happens during the collision. These are just variables I'm creating in service of the problem. And I haven't even read what the question asks yet. I'm just laying out my ideas for what this problem is about. Now, this would be the wrong way to approach a test, but this is homework. So now that I've kind of established those things, I think we have three parts to the problem. In the first part, I see a clear conservation of energy question. So I'm going to do mgh equals 1/2 mv squared. And this is going to be v0 squared. I haven't solved anything. I just know that that's sitting out there, right? In the next part of the problem, the collision portion, that block is going to strike and stick to another block. So m v0 equals m plus m v1. Right? A collision. Now, I am going to pick out the fact that there is a projectile motion problem that's going to follow this. And although I could write my little T-chart out and all of that, this is a pretty basic projectile motion problem, isn't it? I'm going to establish that it's a type 1 projectile motion problem, which means that at the onset of the problem, I know the initial y velocity is 0, right? I can see it that way. Part of the reason for me to do this and say this to you and to identify the type is I don't need the chart. Once I know that the object leaves the table horizontally, I can immediately write down that the time that the object is in the air is 2h over g, capital H. Right? Without having to put delta y, vy naught, vy, a, t. I don't have to do that because I've established the object has no vertical velocity when it's dropped. And in addition to that, I know the range of the projectile will be the horizontal velocity times the time. I'm establishing the parts of the projectile motion problem that I need here. And so every projectile motion problem requires that you deal with time at some point. Now, having said that, I've kind of established a few things, but it's important to note that this velocity and this velocity are the same. And now, because I use the Vx here, I want to figure out if that's related to one of the other velocities that I have, and I think we can all agree that that has to be the velocity there, moving horizontally after the collision. So I will rename this one so that it sticks into my problem better and shows me what's related. Okay, so now I've established what's happening in this problem. I've not solved for anything, but I've established what's happening, and I've got variable names, but I also have put in placeholders that I know I can't have in my answer. So no answer can include v naught squared, and no answer can include v1. Those are not allowed in my answers, but r is allowed, m is allowed, g is allowed, and capital H is allowed. But that also brings up another point. This is not allowed in my answer either. So those can't be in any of the expressions I have because they were not in the list of variables that are there. And they don't always give you a list, but often they will. They will say they express your answers in these terms. So now when it says, what is an expression for the speed of the two blocks if they stuck together during the collision? Well, I see that speed in two places, don't you? I see it here, v1, but that answer would be in terms of v naught, right? Now I could get rid of v naught, but if I do, that answer will be in terms of h. So it's not going to provide me a pathway to get the answer, not in the terms they've given. So I'm going to need a different pathway to get the answer. Well, v1 appears here. That's the velocity they're talking about. Will that pathway provide me an answer that has what I need in it? And it appears it will, because t has stuff in it that I'm allowed to have in my answer. So it seems to me that this is where I'm going to need to go to get that velocity. That's going to be where I start. Now, I'm not saying that what I just did was easy, but this is kind of how you might want to lay it out. You may not know that you had to start from the end of the problem and work backwards, because you're used to starting the problem at the beginning where the thing started. So what I was trying to say to you yesterday is you can pick the order. Now, I picked the order. I picked from the start at the top of the ramp to where it hits the ground. I picked to solve the problem in that order. But when I got here to actually answer the first question, I had to choose the end of the problem as the place to begin. So that's what I'll do. I'll say that r equals vi times the square root of 2h over g. And I'll use that as my starting point to find v1, which is what I'm looking for in part A. So when I do that, I'll find that v1 equals, let's see, r times the square root of g over 2h. And I just divided both sides by the time, and I just inverted the fraction. Is that okay with you guys? Some of you are looking confused, but we're okay with that, right? I always think it's not a bad idea to check your units. G is meters per second squared. H is meters. That's all under the radical, and it's times r, which is meters. So if I look at those, I get no meters in the top and second squared in the denominator. And the square root of that is 1 over seconds times meters makes it meters per second. Because you often will get left with something that just looks like a bunch of letters. And you're saying to yourself, I never know if I have the right answer or not. Well, if you want to figure out if you're on the right track, look at the units. I need units of meters per second here. If when I look at the units, they work out to be the same units, that's a pretty good indicator that you've done your algebra correctly and your substitutions have worked. All good? Do you need to leave yourself a note about what we just did? Now, you actually only asked for question B. I know I did question A first, so let's go ahead and do question B because you've been waiting patiently for me to get there. But I know 2 students who desperately needed the answer to A. So, what is an expression for H, the height of the ramp? It's way over here. So, well, the first thing I could do is solve that for H if I'd like. So let's do that first. Well, I didn't mean to do that. If I solve that for H, I know I'm going to get an answer that I can't use. But let's go ahead and start there. V naught squared over 2G. Now, you know why I can't submit this as my answer, right? Unfortunately, this is in terms of V naught. V naught is not an allowed variable. I don't see a direct connection between V naught and my allowed variables, but I do see that I could substitute in V1 if I wanted. I could eliminate V naught and put it in terms of V1 because there's a link between V naught and V1 here. Does that make sense? So I think that's what I'm going to do next, is solve that for V naught so that I can put it in terms of V1. Now, that's pretty easy too, mostly because M is the same. So it looks like V naught is 2VI, or V1. That okay for you guys? So I can do a substitution now. So I'm going to go ahead and bring this up here and substitute for V naught and get 2VI squared over 2G. I'm closer. And I know that this is going to work because V1 is something I solved. And I have my allowed variables in V1. So it looks like H equals, let's go ahead and do, that's going to be 4 over 2G times, I'm going to put this in there, but I'm going to square it. R squared times G over 2H. All right, I'm pretty okay with all that. I can collect some of these terms, and I think I will. Like, do you notice the G's cancel? I think that's valuable. I'm going to go ahead and cancel out the G's. Are we all okay with the algebra there? Somebody, I see some confused faces. Go ahead, Andrew. So first thing I did is I squared the 2. That's where the 4 comes from. Instead of putting V1 here, I put in what V1 equals here and squared it in my head. Does that make sense? Yeah. So that's why, because that was all under the radical except for the R. So I have R squared, and then everything that was under the radical, I just peeled the radical off and put it next to it because it's squared. Is that okay? Yeah. All right. So I'm going, like I said, I'm going to clean this up, and I get 4 divided by 2 divided by 2. So I can get rid of all of those and get rid of the G's. And I see R squared divided by H is what's left. That just seems like a wickedly weird answer, right? No G in there, no numbers, no M. But R squared is metered squared, and H would be meters, so my answer's in meters, and I want a height, so I think I'm all right with this one. And I know that I am, because I did algebra, and I do algebra, my algebra is correct. But also, there are some things here that might seem weird, like why isn't G in your answer? But G gave the object the kinetic energy, and then G decided how long it would take to reach the ground, right? So G canceled out because the way in which it was used, if G was bigger, it would have gotten down there faster and would have spent less time in the air. So apparently that's all in the same proportion, so we're okay. How's that? Is that enough? All right, is that enough? Yeah. All right. Do you need to see part C?
No.
Okay. Because you're time limited on the test, knowing to start from the end of the problem and working backwards will save you time, right? Because I wouldn't have had to spend the time laying out these procedures ahead of time. I could have immediately said, start with the projectile motion problem. I have where it strikes the ground and I have the height of the table. Now that's going to come with experience, and you need more practice to see those kinds of things. But that's how I would know right away. They gave me where it landed on the floor. They gave me the height of the table. In my head, that means they told me how long it was in the air and how fast it left the table. So for you, that's something you should think about too. Since the parameters were given about the end of the problem, start at the end of the problem. If they'd given us stuff about the middle of the problem, you'd start there. Mm-hmm. Go ahead.
If, let's just say like the time, if you're on the test and you didn't simplify it all the way, it's still right?
There are some things about your simplifications that they won't accept and some that they will. You should always do your best to simplify it as best as possible. Okay? Sometimes they will accept a non-simplified result.
Second to that answer is okay in the terms as H and R.
It is. That's what, but often what it'll end up being, it won't be that will determine that. It'll be, the next part will be sketch a graph of this versus this. Sometimes that's really hard to do if you don't have a simplified answer. And that's how they'll get you to do it or force you to do it. Does that make sense? Go ahead.
I was going to ask if we could do page 6.
I don't know which one's page 6, so stop me when I'm... All right, so question A. What is the velocity of the 5m block when the spring is compressed to its maximum? So looking at the picture, I think the middle picture is what I'm being asked about. But I'm pretty sure we are missing an intermediate step in here. Would you guys agree? Because I think there's a part where the clay ball sticks to the block and gives the 2m block some velocity, but the spring has not begun to compress yet. Does that make sense? Okay. So in an effort to be as expedient as possible and looking at the time and making sure we can finish, you said A and B, right? So I want to do that, and I want to lay out the direction I'm going to go without spending a lot of time. So what I'm going to do is say, well, there is a part of this problem that doesn't involve anything but the clay and the block where there is a velocity after the collision, but before the spring is compressed. Would you agree with that, okay? I'm going to call this velocity V1. No, I can't call it V1. So I'm just going to call it V. That okay? Then the block begins to compress the spring. So the spring applies a force to the left on the smaller block, and it applies the same force to the right on the bigger block. So the little block's going to start slowing down, and the big block's going to start speeding up. Does that make sense? That will occur until the two things are at the same speed. So this, V1, represents the moment that both the 2m block and the 5m block are at the same velocity, but the spring is compressed. That sounds like a perfectly inelastic collision, in that we have two objects that now have the same momentum as the one object had before. So I think I can say 3mv equals 3m plus 5m v1. This represents the spring being compressed and both blocks being slowed and sped up to the same speed. All okay? Now I could solve that for V1, but that's going to have an answer that has V in it and not V naught in it. So that's not going to be sufficient. I'm going to have to express V in some other terms. But I think I can do that because there's the collision that takes place from here to here, right? The clay started this process. Whatever the momentum of the clay was at the very beginning, that has to be equal to the momentum of the clay plus the block, which also has to be equal to the momentum of both blocks when they are moving. All of these states have to be equal because it's all the same momentum. So I could just cut out the middleman entirely. I haven't done that with you guys, but we could, right? So in saving a step, I will, by the transitive property, just do that. Right? Remember all those things. If A equals B and B equals C, then A equals C. It's a transitive property. I'm sure you remember those names. No, you don't. Associative, commutative. You remember all those names?
No.
It breaks my heart. Why was the point of learning it if you don't want to remember it? All right. That suggests that V1 equals 1/8 V0. All right, that was the easy one, right? The next one's harder, but it's not that much harder because energy is conserved here. The energy that was lost by the two blocks didn't just go into the universe someplace. The energy stayed in the spring. Now, don't get me wrong, energy was lost during this transition. Energy was lost there. I can't go all the way back to the original amount of energy, 1/2 m V0 squared. That's gone. That collision took some of the energy away to deform the piece of clay and make it stick to the box. You can figure out how much energy was taken away because you know the final velocity of the system just after the clay stuck to the box. So you know you could figure out how much energy was lost. I'm looking at confused faces. Do you not know that you could figure that out? Let's take a moment and realize that the original amount of energy was 1/2 m V0 squared. This is the amount of energy the clay had. Then, after the collision, the clay and box, the thing I did not solve for, has energy of 1/2 3m V squared. Now, we never solved for V, but we could. It's 1/3 V0. Right? Now, 1/3 squared is 1/9. Cancel out the 3, that's 1/3. Times 2 is 6, so 1/6 m V0 squared. Clearly less, right? Clearly less. But this represents how much energy the system has after that collision. Is that good for you guys so far? I am doing this problem now a different way than I did it before. We've talked about this problem before. The way we talked about this problem before was with the box was going up on the ramp. So I'm talking about it different right now. I want you to think, because we now know how much the block and clay have after the collision. They have 1/6 m V0 squared. How much energy do the two blocks and the piece of clay have after the collision? Well, that will be 1/2 times their mass, 5, 6, 7, 8, times their velocity in terms of V0. Right? This will be how much energy the two blocks have with the spring connecting them. 1/8 squared is 64. Then I drop it back down to 8. Multiply 2 is 16. So 1/16 m V0 squared. That's less energy. But this energy didn't disappear. This energy didn't go into just deforming the clay. This energy is stored in the spring. Do you see the difference? Because it's stored in the spring, I could use that. If I subtract these two, that must be how much energy was stored in the spring. Now don't fret. What I have here is kinetic energy on one side equal to kinetic energy and elastic potential energy on the other. I just subtracted the kinetic energy over. It's still the same statement of conservation of energy. I just talked it out a little differently with you. Right? The energy had to go somewhere. In this case, we can trace it. We know where the energy went. You work that out. You can work the algebra out. I feel confident in your algebra skills. Well, not really, but some of you, I feel confident in your algebra skills. We make those little mistakes from time to time, and we laugh about them, and then you cry about them in a corner somewhere, and it's all okay. There. Since this is the reference point, X, center of mass, will be the sum of each object with mass times its position, added up and divided by the total mass. It's a little messy, I'm sorry, but that's what we have to do for this, right? So M1 is the guy, but he's at 0. M2 is that sheet, and its mass of 5m, but I think that its center of mass is at the center of the plank, so that's going to be at 1/2 of d. Does that make sense? Because I think the center would be there for that. It's a uniform plank or uniform sheet. Then I will divide the whole thing by the total mass, which is 6m. All the m's cancel here. Yeah, it's going to be 5/12. That all right? Cool. To help us with it. And I'll just take that away. This is a good picture to work from. It's the same picture that's in there. Does that work okay? The green line represents where the center of mass is. I will not assume that you knew how to find where that is. So let's talk about that. They, and I mean the people who wrote the problem, and that actually is me, I said that here is where 0 is. And I said the person has a mass of m, and the ice sheet has, the ice sheet has a mass of 5m. And I asked you to calculate where the center of mass of the system is relative to the point I allocated, which is that's our reference point. Everybody good? So that would be a summation. And it's the summation of each point mass, m. Stop it. Who was that? There's Kleenex there, dude. That one sounded pretty messy. Yes, there you go. Anyways, so we add up each point mass and its location away from some reference level, and then we divide by the sum of all the point masses. This gives you the location of the center of mass, as long as we're dealing with a one-dimensional calculation. I think we can treat this as a one-dimensional calculation. We have two objects. Object 1 has a mass of m and a location of 0 relative to the reference level, and then has the ice sheet, mass 5m, and its center is located half the distance away, so that'd be 1/2 d, all divided by, I know that none of you thought to do that. Where did you think the center of the ice sheet was? Oh, wow. Okay, and then the total mass 6m. So this is how we get 5/12 d. All right. That's why the green line is slightly to the left of where the center of the sheet is. Does that make sense? 5/12 is less than 6/12. Now, the simplest thing I want to say from the beginning is the moment the guy starts to walk to the right, okay, they apply a force to the sheet in this direction. And the sheet applies a force to them in this direction. Equal and opposite force. We won't say friction. Maybe they're wearing spikes on their shoes or some garbage like that. We're not going to deal with what that force is for right now. But what's important is that force is probably more effective at moving the guy because he's smaller than it is at moving the sheet because it's 5 times bigger. So, but the sheet's going to move some amount to the left, and the person's going to move some amount to the right. However, the crux of this conversation also has to revolve around the fact that there's no friction between the sheet and the surface, which means there's no external force on the system. If there's no external force on the system's center of mass doesn't move. Okay? However, the location of the center of mass does move. When the guy moves across the ice sheet, is it about the same size? When the guy moves across the ice sheet, they eventually make it to this side of the ice sheet. Well, that means the center of mass is now 5/12 from the other side of the ice sheet, right? Making it 7/12 from here. So the thing had to move 2/12 from 5 to 7. Just a reasonable problem.
I think it is, yeah.
This one? A box of mass 2m rests on a frictionless surface. However, there is a rough patch with a coefficient of kinetic friction of mu naught, a short distance from the box. If a piece of clay is launched at v naught towards the box and sticks to it, how far along the rough section will the box travel before coming to rest? Find an expression for d in terms of m, v naught, mu, and any fundamental constants. All right. There is an intermediate part of this problem that is left out. Can anybody tell me what it is? Go ahead.
Is it the moment the box begins to go onward?
I'm thinking before that, it's the moment directly after the collision. So it's not pictured, but there is this part where a collision has occurred and the box is now moving with probably a reduced velocity. Then it's going to hit the patch and stuff's going to happen there. So we need to find a way to attack this problem. And in this case, I think you have some varieties to your answer. The box is going to slow down due to friction. That should bring to mind Newton's laws, because friction is a force, and whenever we're dealing with forces, we know that Newton's laws can tell us things about it. But Newton's laws can only tell us an acceleration or the size of a force. But if I have an acceleration and it's constant, those two things, well, or if I have an acceleration and I know what the expression is for it, should be able to use it to figure out a change in velocity. The change in velocity is for it to be stopped, right? So I could use Newton's laws and a motion equation to deal with the sliding part. I also know there's the work energy theorem. Friction is going to be done by, the work done is going to be done by friction, and it's going to change the kinetic energy of the box. So I think I could use either one of these two. So you asked, which one do you want to see done? Newton's laws. So the first thing I would consider is that there are three forces that act on the box. I'm going to do these relatively fast. This is old school stuff. Friction is mu times the normal force, and normal force is mg. So I think friction is mu mg. To make this a Newton's law problem, I'd have to say that the net force is equal to ma. Here's where I need to be careful. When we deal with any kind of problem that has forces in it and kinematics, you need to be exceptionally concerned about direction. We wouldn't have this problem so much with work energy, but we will have this problem here. So is D in the positive direction or the negative direction? We have to make a choice. So if we make D in the positive direction, it's important for us to know when we do our net force equation, net force is going to be friction equals ma. The friction is to the left. That means negative mu mg equals ma. Now, I'm going to continue using Newton's laws, but A is negative mu g, The initial velocity is whatever it has after the collision. I'm going to call it V1. I don't want to get this confused with the V naught that's up there already. But the final velocity is going to be 0. And I know that the change in position is going to be d. So if I'm going to make a motion equation, this is where all the variables line up. And I think the motion equation I'm going to use is v squared minus v naught squared equals 2a delta x. Yep. Yeah, I'm sorry, the m would have canceled out. Thank you. So I'm going to go with 0 minus v1 squared equals 2 times negative mu g times d. All good? This is old school, so I'm seeing d equals v1 squared divided by 2 mu g. The negatives cancel. That's good that d works out to be a positive answer. Now, this can't be the answer. Why? That's a lot of mumbling, not a lot of committal. Is V1 allowed in my answer? No. I need to express V1 in terms of something else. Let's look back at our problem. Well, I see a collision. Do you guys understand that? So this part we've done a lot, so I'm not going to spend a lot of time with it, but I will say that m v naught must be equal to 3m v1. Right? This v1 represents how fast the box is going when it first hits that rough patch. So I've got a really clear line on a solution here. 1/3 v naught. So now, plug that in over here. 1/3 v naught squared is going to be v naught over 9. 2 times 9 is 18, so v naught squared over 18 mu g. And we're done. You can do this problem with forces. I would encourage you not to, but you could do this problem with forces. You will need to do forces in a minute anyways. But when you throw the box and it lands on top of this, whatever this is, this sled, it's still a collision and can be treated with conservation of energy because the sled itself is on a frictionless surface. So this surface is frictionless. Because of that, there's no external force on the system. There's forces on the box and there's forces on the sled, but there's no force on the system. So when I toss the box onto the sled, whatever momentum the box has will have to be the momentum of the box-sled system when the box comes to rest against the sled. Does that make sense to all of you? This is a perfectly inelastic collision. So I can just say m v naught is going to equal m plus 3m v final. And that means the final velocity of the system is 1/4 v naught. Everybody good with that? All right. Here's where I think it gets a little tricky. Where does it land on the surface of the sled? Well, there's a couple different ways to do this problem. The way I would encourage you to do it, work energy. The box, slowed down. Work was done on the box, and the work that was done on the box was done by a frictional force that acted as the box moved, and that had to equal the change in kinetic energy of the box. At the same time, friction acted on the sled across a distance that the sled moved. right? Because the sled's going to move during this time. That has to equal the change in kinetic energy of the sled. Now this is an equal and opposite force. So the force is the same on both. It's mu mg, right? It's the force of friction. But the force of friction on the box is to the left as the box is sliding to the right. So mu mg times the cosine, delta x, times the cosine of 180 degrees. That has to equal 1/2 m v final, which is 1/4 v naught squared, minus 1/2 m v naught squared. I don't know if you see where we're going here, but this cosine is going to make that negative, but I'm looking for this because we're going to run out of time. And I'm going to do the same thing over here, mu mg, except this m is 3m. No, this is the force, so it's just mg, times delta xs. It's in the same direction, so that's cosine is 0. 1/2 times 3m times 1/4 v naught squared. All right, so I know all of you are leaving. You want to compare that distance, the distance the sled moved, with this distance, the distance the box moved. The difference in the two is where the box landed on the sled. Because the box went this far, but the sled only moved this far while they were getting up to speed. That's where it landed on the sled. So when the guy chucks the box to the right, he gives the system a momentum. And the momentum of the center of mass of this system is going to stay the same. But I'm pretty sure the box is going to slow down and the sled is going to speed up. Does that make sense? So we're told in this question that this surface has a coefficient of friction of 0, but there is a coefficient of friction between the box and the sled. Does that make sense? All right. The moment the box makes it to the sled, the box begins experiencing a force, and that force is this direction. It's friction. But the sled also experiences an equal but opposite force in this direction. All good? Eventually, the box and the sled are going to reach the same speed. So, let me see. And the box will be somewhere on top of the surface. We don't know where, but they will both reach the same speed. Fair enough? That's just a perfectly inelastic collision. I don't have to do anything more than say that we start with mv naught and end with m plus 3m v final. So the final velocity of the block sled system is going to be 1/4 v naught. It's got to be. Now we could do this a different way, but you won't like it. We could do this using kinematics, but we won't know the final velocity. So we'd have two equations and two unknowns, with one of those unknowns being the final velocity, and we'd eliminate other variables and solve for the final velocity. But you're going to get 1/4. We just have two different accelerations, one acceleration acting on one box and one acceleration acting on the sled. Two motion equations, different accelerations, different starting velocities, same final velocity. We've done this problem before. It was way back in September. But it's one line when you use momentum, so I think momentum's the better way to go. Now, this doesn't tell us the answer to question B. For question B, we want to know where on the sled the object comes to rest. Now that's a good question. We want this. Now, here's the thing. Let's say, for the time being, for just argument's sake, that in this picture, this is where 0 is. And the sled has shifted a little bit to the right, and the box has shifted a little bit to the right. And let's assume the box hit the sled at 0. Everybody following? During that time, the sled moved and the box moved different distances from 0. You guys understanding what I'm saying? During the time that the box was moving, delta x for the box, it was experiencing a force to the left. That was slowing the box down because the box was chucked at v0, but its final velocity was a quarter of v0. During that same time, the sled was experiencing a force to the right. Starting it from no velocity, it eventually made it to 1/4 v0. And it did so in a distance, delta x sled. We know the change in kinetic energy of the box. And we know the change in kinetic energy of the sled. And we know the force that acts on the box. The force that acts on the box is friction, mu mg. And we know the force that acts on the sled, it's the same force, Newton's third law. If we know change in kinetic energy and we know force, this sounds like a work energy theorem problem. It's not the only way to do it, but it's the way I'm going to do it. Because I have all of those pieces. I have the change in kinetic energy and I have the force. And if I recall, and I'm just doing this because you guys have that look on your face, work is for a constant force, the dot product between force and delta x, and the change in kinetic energy. This seems like the right way to go. I'm going to find two different delta x's. I'm going to find delta x for the box and delta x for the sled. And whatever their difference is, that's got to be where this box stopped on the sled, right? That's what this picture says. If I can find this distance and this distance, what's left is where the box ended up on the sled. All right. This one is tricky. No, it's not. So, I wrote that this one is tricky, but it really isn't that tricky, as long as you figure it out. Work is a dot product, though. So I do have a few folks here who really need all the pieces. And so I'm going to make sure we see all the pieces. And I'm writing this out generically before we start. There's my generic work energy theorem. So let's start with the box. Friction, mu mg. Delta x for the box. Cosine of 180 degrees, right? Friction was to the left, but the box moved to the right. Need a picture? Right? We all good? All righty. This has to equal 1/2 mv final, 1/4 v0 squared, minus 1/2 mv initial. Now they gave that to us. All right. Sled. The sled's experiencing a force. What force? Mu mg. It's still a little m. It's the same force. A lot of people put 3m in here, but that's not the right thing to do. The force is about the normal force on the little box. That's what creates friction. So it's still mu mg. Times delta x for the sled. And that's going to be cosine of 0, right? Because that force is in the direction of motion. And it makes sense, guys. We needed this one to be negative because it slowed the box down. It lost energy. We needed this one to be positive because it sped the sled up. Increase in energy. And this one will be 1/2, be careful, 3m right? Mass of the sled, or is mass sled 2? 3m, times 1/4 V naught squared minus 0. Right, we have to use the mass of the sled. This is the inertial mass of the system, so we need its inertial mass, which is 3m. All good? All righty. I want delta x in both. I probably could use an intermediate step, which means I'll probably have to, figure out one of these fractions. So let's do the fractional side here first. All of those terms have an m v naught squared in them. But I'm going to have 1/4 squared is 1/16, and 1/2 of 1/16 is 1/32. And the other one is just 1/2, so that's 16 32, and I'm subtracting them. So negative 15 32. That all good for you guys? All right, that's a lot. And that equals mu mg delta xb cosine 180. So negative, and just get that out of there. All right, I can cancel the m's. So I have an m in both terms. But now I just need to get rid of the negative sign, and delta xb equals 15 m, no m, I canceled it out, v naught squared over 32 mu g. All right, that's my algebra. All good? We all okay? Let's go ahead and do this one. 1/4 squared is 1/16. Times 1/2 is 1/32, so 3 32. Oops. M v naught squared. I don't think there's anything I can do about that. So I think we're going to stop right there. But I can go ahead and cancel the m's. Can get rid of that cosine 0 degrees. I can solve for delta xs, and that's going to equal 3 v naught squared divided by 32 mu mg. All right. Subtract. So I am going to subtract, and I have the same v naught squared over, I forgot, there's an m there. Let's get rid of that m. I'm sorry, bad Mr. Shelton. Be better. All right, so all of these terms have a 32 mu g in them. But I have here 15 minus 3. Right, we're subtracting this one from this one. I mean, we're just doing arithmetic now, but this is going to be 12. And 12 and 32, do they share a common factor? 4, right? So that will be 3/8. One way to check your answer, because this is supposed to be delta x on sled, is to check. V naught is a velocity, right? It's in meters per second squared. Mu is the coefficient of friction. It has no units, so that's a unitless quantity. But g is going to be in meters per second squared. Now, if I look at this, that's a meter squared per second squared divided by meters per second squared. That's an answer that's in meters. I'm supposed to get a displacement. Now, this doesn't prove if you have the right answer, but this will pick up algebra mistakes, right? Like if I had left the m in the denominator, there would have been some kilogram thing stuck in there, and I would have known something's amiss, right? Those kinds of mistakes get picked up by this. So it's not a bad way to go, because it gives you something tangible you can do to see if you're on the right track. All right.